So before I start, my name is Vahagn Mkhitaryan, and I'm at Purdue University. I'm a research associate there working with Vlad. And but before I start, I would like to thank the organizers for this opportunity to present our recent collaborative effort results. And Shankta already spoke. There are many teams now involved in the project, and but main two teams to really enable the work, and we could progress with the experiments and also the theory where Quora and recently Amazon, because we access the Quora machines through Amazon. So Shankta from Quora already presented, but I also want to mention specifically Milan and Fangli, who were main driving force behind the theory of the work. So I wanted to mention them, and also Peter will just speak after me. He was the enabling force from the Amazon side, bracket side. Okay, and the work is one more example of how one could use Quora's Aquila machine to do many-body simulations. In this particular example, we are looking at the phases, quantum phases of the Shastry Sutherland lattice, which is a specific lattice I will introduce in a second. And it's this kind of Ising type of interacting spin system with the spins located at the lattice shown on this picture on the left. You can think of the lattice as equivalently as a square lattice, but with this diagonal interaction J2 being different from the other diagonals that they've defined here as a J3. And we started this project about the same time as Aquila came online in 2022, and maybe Shankta can confirm later, but we were one of the first collaborators, academic collaborators with the Quora team to try to study many-body dynamics of the interacting systems. And the one reason why we picked this project was actually exploratory, because this model was known to be exactly solvable. At least the classical limit of this model was exactly solvable, and the ground states were studied well and were known that it supports certain fractional magnetization phases, and the phase diagram was well known, and we could benchmark the results from Aquila machine to the known results and study. But as you will see, this was not the only result we have, but there were some surprises that came with that, specifically because of the Rydberg Hamiltonian we were using to study the system. But the second reason why we chose it was because we could realize this interacting system on the real materials, and people have been studying this fractional magnetization state in these real materials. And again, if we could prove that we can study such systems, it would be also one way of showing the path that you can approach such studies, many-body interacting spin systems, using the quantum simulators currently available, even the analog ones. And the third reason for this was that there were previous studies of this model on D-wave machines, D-wave annealers, and people have actually observed some of the classically known fractional phases, in particular this 1/3 phase. And some of our collaborators were authoring this paper. So this knowledge from them would also help to push the progress forward. But again, we wanted to use the Rydberg system. I had a few slides on how the system works, but because I know that there were a lot of talks on such system previously, and also Shankta introduced, I skipped that theory part, the interaction part. So we'll jump right away on the describing the system with the Rydberg atoms. And the Hamiltonian of our system would be looking like this. So you have the initial drive part of the Hamiltonian shown here, drive part of the Hamiltonian, but you also have the interaction term that will be given by these three type of interactions. Nearest neighbor interaction that you have on this lattice will be this short edge with the V1 interaction strength defined by the distance of the atoms. And you have V2 interaction strength that is on this diagonal of the short diagonal of this rhombus. And you have this fixed V3 interaction strength that's dictated by the topology of the lattice, and by fixing the V1, because just the diagonal of this square will be fixed by the V1. The controls we have over our system will be the angle of this lattice, which will control the V2 over V1 ratio. But also we have the detuning part, which by the time we were working on the Aquila system was still global. We didn't have yet the local tuning implemented, but currently it's available. So for us, it will be just local, essentially transverse magnetic field alternative to what you know from the classical spin system. So it's just acting as a transverse magnetic field applied to our spin system. And those are parameters we can control. And also, of course, drive is going to be globally controllable in time. It will be fixed in space, but you can control in time. Those are parameters to use to prepare the ground state of the system using adiabatic approach, state preparation approach. And if you look at this part of the interaction part of the Hamiltonian, it really resembles the classical Shastry-Sutherland model of the interacting spin-sizing type of interactions. But on top of that, and of course, the classical phases, if you calculate the phase diagram using only the classical part of the Hamiltonian, you will recover these fractional phases. You will have 1/3 fractional magnetization. Some phase that it's called the linear phase. It's just the ordered phase where the atoms or the spins on this diagonal bond are antiferromagnetically ordered, so the entangled state, but they ordered row-wise in the lattice. So this lattice, the first thing we did, we basically tried to reproduce the classical results with our simulations. But on top of the classical Hamiltonian part, we always have the Rabi drive with a Rydberg system. And that would introduce some fluctuations in the system. We will try to rotate the spins, and that rotations will introduce fluctuations in the system. And what that brings into the system is that these fluctuations may stabilize some of the phases, classical phases that were known to be living at the boundaries. There are many degenerate fractional states that live at the boundary between the 1/3 phase and the nil phase, and the cleaner phase and the nil phase, which are not visible in the classical limit. But as soon as we had these fluctuations enabled in the system, the fluctuations enabled the stabilization of these phases in a much larger mode volume in a phase diagram. And we started observing this too. These are all DMRG calculations. So we started initially with the numerical studies of the system before we did the experiments. And in this initial DMRG calculation, we started seeing these two new phases appearing, which we established to be 2/5 and the 4/5 fractional phases of the system. But on top of that, this originally ordered linear phase starts to be fluctuating, starts having more quantumness in the system. Entanglement of the system is increasing. And that's the second prediction came from the theory. So two predictions that we focus on is that we are observing new phases that were known to be only living at the boundary with 0 phase volume. And the second prediction was that the originally linear phase becomes more quantum. So we introduce more quantumness in the system. And one of the indications for the quantumness of the system is, of course, by controlling the interaction strength on the van der Waals interaction strength with respect to the Rabi term. By reducing the Rabi term, you would reduce the fluctuations you introduce in a system. And that should reflect into the system rendering or going towards the classical phase diagram. And we clearly see this behavior from our simulations. When you change this control parameter, which essentially controls the ratio between this V1 interaction strength and the Rabi term, Rabi frequency, then you would see that as you make the V1 larger than omega, the classic this originally observed two phases, fractional phases, start to disappear, and the mode volume of those start to be shrinking, and the phase diagram goes to the classical limit as expected. So that was one of the indications. And for the quantum dimer phase, which we coined quantum dimer phase, one way of checking that you're introducing quantumness in the system was to define this dimer flip operators we call D, which essentially checks whether dimers are occupied, whether you have these antiferromagnetic ordered dimers in your system. And if you would have ordered state, you would expect that the ensemble average of this expectation, if it's ordered state, expectation value should be plus or minus 1. And if you take the square of that, which removes the phase of the entanglement of the dimer bond, then you would see just 1. What we see from the experiments is that these dimer bonds are actually fluctuating, and the expectation value of this D operator, dimer occupation operator, is 0. And its square is always going to 1. This was one of the indications that we introduced fluctuations in the system. The dimers are not anymore ordered. dimers, but they fluctuate between two possible realizations or many possible classically degenerate realization of the dimer map over the lattice. And the second indication was when we checked the dimer correlation spatially, so between between the dimer sites, different dimer sites, and we've seen that these dimers are classically random. Essentially, the correlations exponentially decay in space as a distance between the dimers, and both in 2 dimension and also in 1 dimension. Another thing, because in numerics we can do different type of correlations, it's available to us. We checked what's the phase of this entanglement on the dimer phase, and for that we just defined this dimer flip operator. If you act on the dimer, it would just flip the dimer. So if the atom initially is excited at this node and in the ground state on the second one, when you apply that operator, you should flip the dimer. And we've noticed that these dimer flip operations are highly correlated because you see large non-diagonal elements in the correlator map. And that was also a second indication that essentially we have dimers, quantum dimers in our system, but also these dimers are correlated. The extent of correlation is large. Okay, but in our mind, we always had this goal to do this study also experimentally, and we should have think about how we are going to differentiate these different phases from one another, because the data we have accessible to us from the machine is just binary data telling what was the state just before you quench the system. And one way of looking at the phases, obviously defining this number correlator, the structure factor, essentially, which is the Fourier transform of the number correlator matrix. And this, because each phase would have different ordering, then the symmetry of those ordering will be well-defined peaks in the Fourier transform in the structure factor. And by looking at the amplitude of this structure factor for the given symmetry points and see how this is distributed in the phase map, you could potentially differentiate different phases from one another. These are the phases we were looking at, and you can see that they have distinct symmetry points in a Fourier space, and that's what we used in experiments to study. But one need to be careful in experiments because when we do DMRG calculation normally, I know many of you have already done such studies, you would pick up because you're simulating effectively periodic lattice, infinite lattice of interacting system. And normally this is done by just doing partially periodic boundary condition. You wrap the system over the cylinder and by letting the sides, the second dimension to be open boundary condition. And depending on what is the lattice size you're taking in this open boundary direction, you may or you may not be commensurate with the lattice ordering you're expecting for your phases. For example, here we have two phase diagrams calculated for the same interaction parameters, but the lattice sizes are slightly different. And you see that for this initial one, the 1/3 phase was commensurate with the lattice, so the entanglement entropy, which we choose as a numerical order parameter for our studies, it has low entanglement entropy. While the same interaction parameters for this lattice sizes, which is not commensurate with 1/3 phase, gives much larger the entanglement entropy. It's essentially, this finite size effects are affecting the phase diagram of our system. So when we would do the experiments, we needed to be careful with this fact that finite size systems would introduce problems or errors that we need to take into account. Another effect that you might expect is the domain size appearance in the system because of this non-commensurability, and that obviously would reflect to incorrect representation of the structure factor of your system, because this Fourier components of these domain walls would produce other peaks that would not be real, that would not be the same as, it will be obviously real for the finite system, but it's not what you were looking when you are studying the infinite system. So we came up with several ways of essentially compensating this finite boundary effects. And initial thoughts for us was to use the local detuning to try to compensate this. Essentially what happens at the boundary is the atoms are trying to order themselves in the antiferromagnetic order to minimize the energy. And while the ordering that you were expecting, you could have a ordering where two of these boundary atoms are are essentially need to be remaining in a ground state. And by applying local detuning, you could just bias those two atoms to be going towards the ground state a bit, or remain in the ground state a bit longer than the other atoms. So ordering happens before the boundary tries to pin itself to a specific antiferromagnetic order. But at the time we implemented this experimentally, we didn't have the local detuning available to us. So the second option you can think of is just add extra atoms near the positions where you want two atoms to be in a ground state. Essentially, by having extra atom that can be in the excited state, you are minimizing you're essentially lowering the energy requirement for this ordering, and the ordering becomes possible in that case. And for this, we did some numerical simulations. So these are two examples. The two rows are two examples of the phases. The first one is 1/3 phase with this extra atom tuning strategy, and the second one is a 2/5 phase. And we've seen that we essentially can prepare the state by adiabatic process we were thinking of to prepare the phases, and you could see the well-defined peaks when you have so we have these extra atoms, but everything else is open boundary. We don't do any special trick on that. All the atoms are treated equally. Just we put this atom on the side, just minimize the energy requirement for these two atoms to be in a ground state. And on the top side, because the ordering will be antiferromagnetic, you don't need to bother much. So it's only on this side. It's one of the sides you can pick up. So we did this initial state preparation studies on the system, and we picked up this relatively smaller lattice size. It was 8-on-9 and 8-on-8 lattices. And we could successfully, the first row shows you the DMRG calculation I showed in the previous slide, and the bottom one is the experimental results. And for these fixed interaction parameters, we could actually successfully prepare the phases. You can see the ordering corresponds to what we were expecting from the simulations, almost 1-to-1, and the Fourier components are where they are expected to be. So that was a good sign. And of course, the second was to check whether the predictions of the 2/5 phase were actually realizable in the system. And it turns out, yes, we could prepare also the 2/5 phase. And that was the first proof of these two extra phases being stabilized in the system. And we could access, and we could see this experimentally in our studies. And the quantum dimer phase similarly was present, and we could see the correlations as they were expected to be. So the left is the experiment, and the right is the simulation results. Okay, and if you check this dimer occupancy operator, the expectation value, you can see that experimental results, which are on the right, reproduce the behavior we were expecting from the quantum dimer, not from the ordered linear phase. This was a proof also that the quantum dimer phase was also present. So with these small experiments, we could prove that both predictions were there. So the two new phases appear, but also the dimer phase was more quantum, has more entanglement than it was on the classical system. And then we proceeded with studying larger phase diagram area to see if we can actually produce these different phases and the phase maps as we see from the simulations. This was one example just to test how the system behaves. I did the line cut across two different phases, and you can see as we move along this line here, you go from the 1/3 ordering to Néel ordering, and the two peaks, the Fourier peaks, are merging in the center where the Néel phase is supposed to be. Those were all the indications that we are ready to do the experiment for larger phase space. And we picked up this region of the phase diagram for our study. Obviously, each point is a one-state preparation. You have 1,000 shots or 500 shots, depending on how large you want your statistics to be, how good your statistics to be. And it's an experiment. It's an expensive experiment, so you need to have in mind you cannot do large arrays or high resolution. So you'll have to pick up a specific region of interest. But this is good enough. We could see most of the phases we were looking at. And so we started exploring this phase diagram of the system. And if you try to plot the Fourier components of the structure factor for the 1/3 ordering phase diagram was selected by this white rectangle. And we did experiments with 3 different boundary conditions. So one was we picked these extra atoms to be trying to bias the system towards the 1/3 phase. The second is biased towards the 2/5 phase. And the last one is with open boundary without any extra atoms, just to see how the system behaves and how critical is the role of the boundary pinning and this extra atoms on the system. And when we look at the structure, the order parameter for 1/3 phase, with these three boundary conditions, we can see that obviously 1/3 pinning is favoring mostly the 1/3 phase very nicely, as it was expected from the simulations. In the 2/5 pinning is slightly affecting the phase diagram, but you can still see the large amplitudes wherever you would expect that 1/3 phase be. The completely open boundary condition ruins a bit the well-defined boundaries of the phase, but you still can see a large region where the 1/3 phase should be. Because again, in the Fourier transform, if you have extra ordering at the boundaries, and if the ratio of the boundary to volume atoms is not large, which is the case in our experiments, we only have 112 qubits, which is, I know it's large for some cases, but for this 2D, two-dimensional phases, but I guess it's not still enough. And the boundaries are significantly affecting the ordering of the volume atoms. And so we could prepare the 1/3 phase, and we look at the order parameter of the 2/5 phase, we could see that we are expecting the 2/5 phase appearing actually wherever it's supposed to be. Again, there is a significant effect from the open boundary case. But you can see when you favor the 2/5 ordering with the boundary pinning, the volume of the 2/5 order becomes much larger, which is again indicates that this favors the 2/5 phase. And also, 2/5 phase is a little bit more quantum phase, and it's harder to prepare than the 1/3 phase, more ordered 1/3 phase. And if you look at the Neal phase, you can see the Neal is again in the area where you expect the Neal to be, but if you compare it to 2/5 phase, there's significant overlap between Neal and the 2/5 phase, and that's because again finite boundary effects, and the boundary atoms are trying to pin themselves more towards the Neal ordering, and when you do Fourier transform, you pick up the components of both, and we could see this effect essentially in the numerical analysis of the data by fitting the peaks of the Fourier transforms into Gaussians. Just the two Gaussians are overlap, and you pick up signatures from both phases at the same time, and it's a little bit hard to differentiate the 2/5 phase from 1/3 phase. But when you look at the specific points with a large statistics, as you saw in the small lattice cases, you can actually reproduce the ordering as you were expecting. And obviously, when you look at the quantum, this dimer occupancy expectation values, you can see that dimers appear, dimer occupancy amplitudes become large wherever you would expect the dimer phase to be on this corner. And that was the second indication. And now we are in this last stage of our experiments, it's still going on. We want to basically prove this transition from quantum to classical. By going to more classical limit, we should be able to quench this to two new phases, 2/5 and 4/5 phase, and go towards a classical phase diagram. And that should be last experiment we are preparing currently. And with this, I want to thank again everyone for listening and my collaborators, because this work wouldn't have been possible without all of you and your contributions. And I want to hand maybe talk to Peter to continue showing how the systems can be accessed through Amazon. The second option of accessing the machine if there is no direct contact with the Queries team. Okay. And I'm open to your questions, obviously. Thank you. Yes.
One's anti-ferro?
Now, all of them are the same sign. Yeah, you can control the interaction strength between the diagonal terms and non-diagonal terms, essentially.
I see. So when you're sweeping like the V2 over V1,
I'm changing the angle here. Yes.
Right. So the shape of this is changing ever so slightly in the hardware.
Yes. Yes. Yeah, you're welcome.
Any more questions for Vahagn? Hi, yeah, thanks for the talk. I was wondering, so here you were considering sort of I guess, a perturbation of a classical model of which you know the phase diagram. Do you think
essentially it turns out to be the perturbation by this extra rabbit term that is sigma x perturbations to your system?
Right, you're right. So I was wondering whether you have any intuition what would happen if you kind of change some of these ZZ terms to, for example, XX, and whether you think that would be possible to do on such devices, or specifically this device?
I think currently the Kila doesn't have an option of you can do the quenching type of dynamics. I don't know how easy it will be to realize. Maybe Shengtao will be more to comment on that. But it's known that the same lattice structure with the anisotropic Heisenberg type of interaction would actually have much richer physics in it. You might have even more quantum phases, even quantum spin liquid phase. You might be observing topological phases in the system. And it's known. I mean, and then also there are material realizations for that type of thing. Just the same lattice, but Heisenberg type of interaction, anisotropic interaction.
Just to answer on the kind of implementation side on Aquila, so it's not as easy to implement, other like XX terms on the device as you know the Rydberg Hamiltonian, but you can always do kind of quinches and floccate type of thing, but that's always associated challenge, in terms of coherence time and all of that. Yeah.
Also, you might go more excited states of the system, and it's hard to disentangle the effects that you're seeing. Yeah.
Any more questions?